welcome to Wednesday's edition of Cracking the Cryptic, where with some trepidation I'm going to attempt this puzzle called Archery Target by Nihilian. Now Nihilian is a fantastic setter. I love their puzzles, and Nihilian wrote to us recommending that we try this. Our testers got absolutely nowhere with it, and I had a look at it on Logic Masters Germany, and I've noted I think it's only been solved 5 times ever, which is not very many times. And the comments from those people who have solved it are along the lines of, this was absolutely brutal, but it was one of the best puzzles I've ever solved. So I would like to be able to solve it, but I do think this might be a step too far for a video. But we'll see. I'm going to give it a go, and I have another puzzle on the back burner, so if I fail to solve this, you will never see this video, and I will just do the other one instead. So yeah, I'll read the rules of this in just a second. First of all, what the other things I need to do today, I need to say a very, very happy birthday to Nicole over there in North Carolina. Now, Nicole, your boyfriend Nathan got in touch with us and said that you've been watching the channel, I think, since the Miracle Sudoku, yeah, that you're regular watchers along with your cats, Phineas and Phoebe, and he even sent a photo of the cats watching Cracking the Cryptic, which amused me. So yeah, I hope you have a brilliant day, of course, with lots and lots of cake. Next bit of news, we've mentioned this a couple of times over the last 2 days. We are streaming on Friday night, 10 o'clock UK time, as part of the Cerebral Steam Experience or something. So I don't know what the Cerebral Steam Experience is, but we are part of it, and we're just trying to decide which Cerebral game we're going to stream. Mark and I have been disagreeing quite vehemently about that. Anyway, watch this space. We'll announce it on Twitter as soon as we make a decision, and it's the 18th of May today, which means you've still got 2 days left to get your solutions in to our Patreon reward for May. That's the Equal Sum Lines hunt that many of you, many thousands of you actually, have been enjoying. And yeah, if you want to be in with the chance of winning the prize, we need your answers by the 20th. Now, that all said and done, why don't we have a look at this extraordinary puzzle? You can see we don't have much information by way of given digits, and I've read the instructions. I don't think we have much information by way of instructions either, but here are the instructions. We have got normal Sudoku rules apply. The grey line in the central box is a thermometer. Digits along that thermometer must increase from the bulb to the tip, but the positions of the bulb and the tip are hidden, so this is a particularly annoying thermometer. So in fact, let's work this out. If we worked out that this cell was the bulb, how am I going to show that? Maybe like that. Yes. Okay, so if we worked out this was the bulb, this is an 8-cell thermometer, so this could be a 1 or a 2. Let's say it's a 1. Then this could be a 2 or a 3. Or, oh, I know, it could go either way round. Oh, good grief. Yeah, okay, so then we don't know which way round it goes. So this one could be a 2 or a 3. This one could be a 3 or a 4, or it could go the other way round and it be increasing in this direction. So yes, I think what we can conclude at this juncture is that this thermometer in the middle of the grid is not the most useful thing we've ever seen in a Sudoku. However, the next bit of the rules is, I think, where the complication arises. In the outer 3 rings, the sum of the digits along a ring between 2 nines must always be the same throughout the puzzle. For the avoidance of doubt, those 2 nines could be the same 9 if a ring has only a single 9 in it. Now, there is an example Nihilian made here, which I think is at least worth our attention. So I see. So Nihilian has filled in the thermometer in the middle. I can see that that is increasing. And there are 9s in the rings. And what we're being told is that the green lines in this puzzle would all have the same digit total. So these cells here along this blue ring would add up to the same as those 5 cells along the blue ring, would add up to the same as these in the perimeter. So every green line has to have the same sum of digits on it. And I think that this rule that says, for the avoidance of doubt, those two nines could be the same 9 if a ring has only a single 9 in it, is to deal with this 9 here. So that 9 is the only 9 on the red ring. And so we're at this 9, we go round the ring until we find the same 9 again, but that's this string of greens still counts as a green string for the purposes of this rule. That's the rules. That apparently, I mean, one of the most incredible things about that is that that leads to a unique solution. I could see how, with 3 months of effort, you could deduce some things about some properties about the rings. But I have a lot of difficulty believing that that rule yields a unique solution, let alone a solution findable by a human being. But 5 people have solved it, so I guess it must be possible, and it must indeed be true. So I think we can say, before we start, that Nihilian has come up with some sort of masterstroke here, and it would be lovely if we can work out how to solve the puzzle. With that, I am going to have a go. Do have a go yourselves. The way to play is to click the link under the video as usual, but now I get to play. Let's get cracking. So, right, let me read the rules again. In the outer 3 rings, okay, so there's 1 9 in the middle box, isn't there? So in the outer part of the puzzle, the bit that's consumed with the archery rings, we've got to put 8 9s. That is something that I can see to be true, but we have absolutely no clue how to dispose those 9s around the rings. It's not even, I thought maybe I could deduce something about the outside ring then, but I can't even deduce very much about that. Although this outer ring contains 4 Sudoku units, by which I mean there are 2 rows and 2 complete columns in the outer rings, you actually can't say that there are therefore 4 9s in the outer rings, the outer ring, because you could put a 9 in the corner. And if you put a 9 in the corner, you could put a 9 in that corner, and now I only have to have 2 9s in the outer ring. So the outer ring doesn't have to have 4 9s in it, it just has to have a minimum of 2 9s in it, which means I've still got to put up to 6 9s in the blue and the orange region. And I suppose I can never put more than 4 9s in a region. So if there were 2 9s in the grey, there would have to be 9s in both of the other regions. Is it? I'm just wondering if it's necessary that there are 9s in all rings. It's clearly necessary that there are 9s in the grey ring, because I can't not have any 9s in these, because that would imply, for example, row 1 has no 9s in it. Is it possible there's no 9s in a blue or an orange ring? Oh, is Phistomefel in point? Hang on. So this is the theorem. Many, perhaps most of you will know the Phistomefel theorem, and the theorem is that the cells that make up the orange ring are the identical digits to the 16 cells in the corner of a grid. Now, if it turns out that I think this is important, I will prove that for you. But let's just think about that for a moment and take it on trust that it's true. So whatever I put in the orange ring has to go in the 2x2s. So if I did put 4 9s, if I put 4 9s in the orange ring, I would have to put 4 9s in these cells. That's not even restricted, is it? That's not restricted. Okay, right. Maybe it's not Phistomefel. So, sorry, I am not understanding this at all. So we know that there are at least 2 9s in the grey. And there are some number of 9s which cannot ever be greater than 4 in any individual ring, because obviously the blue ring contains row 2 there, row 8 there, column 2, column 8. So I can't put more than 4 in, because I'll definitely repeat a 9 in the blue if I do that. Right. I have a horrible, horrible suspicion this is going to be very mathematical then. So what I'm wondering is if we can back into the value between the 9s here. So imagine there was a 9 here. Oops, I want to put a 9 in there. Imagine there was a 9 there and a 9 there. Hang on, am I going mad here? There are somehow or other, there are 8 9s in the top of this grid. Not in the top of this grid, you understand what I mean, in the outer bits of the grid. Now, if we think about the maths of a Sudoku grid, and I think this applies to any Sudoku grid, we have to know the secret to understand what I'm about to say, so I'll just let you know the secret. Now the secret is, and this is an important secret, and the secret is that any complete row, any complete column, or any complete box of a Sudoku, because of the rules of Sudoku, contains the digits 1 to 9 once each. If you add up those numbers, you get 45. So a complete Sudoku grid, which has 9 rows in it, adds up to 405, which is 45 times 9. Now, we know that there's 1 9 in here. Well, there's 45's worth of digits in there. So in the 3 outer rings, there are 360, or digits summing to 360. Oh, this is a problem. This is a problem. I was about to say, let me think about this a second, hang on. What I was going to do was I was going to say there are 8 9s in the top of this, or not in the, I keep using the top, but you understand what I mean. There are 8 9s in the rings. And so I was going to deduct 8 times 9 from 360, which would give me 288. And I was going to say that because those 288's worth of digits have to be disposed equally between the 8 9s, then the value between the 9s is going to be 288 divided by 8. I don't even know if that factorizes exactly, does it? Oh no, it does. It does. 288 divided by 8 is 36. That is quite, actually that's quite persuasive. 36 is quite a lovely number in a Sudoku sense, not involving a 9, because that is the sum of the digits 1 to 8. But the flaw in my logic here, and this is why I'm worried about this, is that I think that's all true if every ring has a 9 in it. But what would happen? Let's imagine that the blue ring has no 9s in it. Then I'll put 4 9s around the edge, something like that, and I have 4 9s around this edge, something like that. I'm probably messing this up. I am messing it up. I've totally messed it up. Ignore the Sudoku implications of this. I want to think about the fact that I'm claiming that I can do the maths on 288, but this would not work in this instance because there would be no 9s in the blue ring. These digits, they have nothing to do with 9s. So when I'm dividing my number by 8, it's not 288 I should be dividing, it's 288 minus the blue ring I should be dividing. And that is a problem. So this logic around 288 divided by 8 is valid if and only if every ring has at least a 9 on it. If every ring has I think it's all right, isn't it? If we have 1 9, if I had 1 9 on the blue ring, then I'm adding up those cells and saying that whatever those cells add up to is the same as if we had 9 here and 9 here. It's the same as those. So that's fine. Because and I'm saying there would be a 9 in this ring, and so it would be the same as that. So we'd be saying that those, in fact I can do it with lines, we'd be saying that those, and this would all have to have the same total. But that's fine, because once I've sprinkled all the rest of the 9s in, we'd always be summing all of the digits in the rings. The problem comes when we don't have a 9 on a ring. That logic around the... So how am I going to prove that? I have to prove that there is a 9 in every ring of a Sudoku. How do you do that? And if I can do that, then the logic that gives me the 36 number is correct. And that 36 number is massive. Because that's basically saying that you can't have 9s very close together at all. I mean, that would be impossible, I think, because 8, 7, 6 and 5 only add to 26. Yeah, so we would have quite a big difference between the positions of the 9s in the grid. They'd have to be very well separated. So, how do we prove that every ring of a Sudoku has to have a 9 in it? I've got no idea how to prove that. I can prove it for the outer ring. I can definitely prove it for the outer ring. That's easy. I don't know how to do that. This might be where we get completely stuck, I'm afraid. If there is a proof of that, I don't think I know it. I'm just sort of testing my memory here. Have I ever heard of a proof of something like that? I don't think I have. It seems like it's related to Phistomefel if it is a proof. That every ring in a Sudoku must contain... It doesn't even seem to be very necessarily true, actually. Because surely... No, it's not true, in fact, because I've certainly done puzzles before where the Phistomefel ring hasn't contained a digit. Because that's the whole basis of potato head potato heads thing around the knight's move thing that ends up with anything that's not on the Phistomefel ring ends up in the middle of the grid. So yeah, okay, so it's, oh, this is a problem. This is a problem then, because now this 288 logic is nonsense, isn't it? Well, it's not nonsense, but it's very much an income. So so maybe we've got to turn this on its head, actually. Maybe we've got to turn it on its head and prove, if we can prove the gap cannot be 36, hang on. Yeah, that would work. That would work logically. So, if we can prove that the gap between 9s cannot be 36, then we know that our 288 was not the right number. We shouldn't have been dividing 288 by 8, we should have been dividing some other number, which implies that one of the rings must be missed out. And that would be interesting as well. So, how do we prove that the gap between 9s in this puzzle is not 36? And the only way we can surely do that is using the outer ring, because we don't know anything about the inner ring. We don't know. Well, I'm hypothesizing they have 9s on them, but I don't know how many 9s they have on them. And I'm not... So... Right, okay, well let's do the maths on this then. So the outer ring is the perimeter of a Sudoku. Now we do know things about the perimeter of a Sudoku. I'm just going to highlight those cells in green because this is going to matter. We know that the sum of the outer of the perimeter of a Sudoku is equal to 45 for that row, 45 for that row, 45 for this column and 45 for this column. Now if you were focusing, you'd have noticed that those 4 cells there were in 2 different things. Obviously in row 1 and column 1 this digit appears twice. So to calculate the sum of all the digits in the perimeter of a Sudoku, we can't just multiply 45 by 4 and say it's 180. It's not. It's 180 minus whatever is in the corners, because they have effectively been double counted. But it's not 180. Right. Okay, that is worthy of note. So what we can actually say now, I think, if there were, right, yeah, this is right, I think. What would happen in this puzzle if we're in a world where every ring has a 9 in it, and so we know that our divider, we have to divide the 288 by 8. We got 36 for that, so we know that we have to put 36 between any 9s in the puzzle. Now we know that the perimeter has at least 2 9s in it. Could the perimeter have 4 9s in it? And the answer must be no. Because if we do put 4 9s in the perimeter, then what we're saying is that the perimeter of this Sudoku would sum up to 180, because we're saying that there are 4 9s, which are 36, and 4 lines, which individually sum to 36. In other words, we've got 5 times 36, which is 180, and we've just said that's impossible, because we have to put positive numbers in the corners. We can't put 0 in all 4 corners of the Sudoku. So it's not right. So if we have a 9 in each ring of a Sudoku, then the outer ring doesn't have 4 9s in it. Now, what would happen if it had 3 9s in it? Let's just get rid of that 9. How much does that change the maths by? If it's got 3 9s in it, then the perimeter would sum to 27 and 3 lots of 36, which is 118 plus 27, which is 145, isn't it? It's 145. Yeah. Going a bit crazy, but yeah, I think it's 145. Now 145 oh, I see. Right, this is amazing. Right, okay. Right, I've done it. When I say I've done it, I've done the most minor thing, but I have done something. Right, what is the maximum value I can put in the green cells? And the answer would be 8s and 9s. I couldn't put 4 9s in the corners, obviously. They'd see each other. But I could put 2 9s in here. And I know it looks like I can't because of the way I've positioned these 9s, but I could obviously move these 9s around. I'll put 2 of them in the corners. So I could put 2 9s here and 2 8s here. That would be that maximum number of maximum size of digits I could put in any corner cells of a Sudoku. Well, 8 plus 9 is 17, and 2 lots of 8 and 9 is 34. And if I deduct 34, which is the maximum I can put in the corners, from 180, I get 146. And 146 is more, here is a knowledge bomb, than 145. And so, but we said that if there were 3 9s in the perimeter, and we're in this paradigm where the gaps between the 9s add up to 36, we need the perimeter of that Sudoku to add to 145, which we've just proved is impossible because the minimum value of a perimeter in any Sudoku is 146. So this proves that you cannot... Well, it proves 36 is not the number. That's what it proves. It's taken me half an hour to do it. I'm going to have to remove all my pencil marks because they're all nonsense. But we now know that 36 is not the number. So let's just check the logic on that. We said if each ring has a 9 in it, at least one 9 in it, then those digits in the outer rings, which sum to 360, that's right, deduct out of that the 8 9s, so deduct out of it 72, we get 288. But if every ring has a 9 in it, we're summing all the digits between the 9s to get to that 288. So we can divide 288 by 8, we get 36. There must be 36 between each 9, and we've now proved that cannot be true in the outer ring, because with 4 9s, that outer ring would add up to 180, which is impossible in any Sudoku. With 3 9s or less, you're adding up to a number that's less than 146, which is the minimum. So nothing works. And if nothing works, we now know that one of the rings in this puzzle has no 9 in it. There we go. We have deduced something sensible. I almost feel I should stop the video there. I'm going to make another video in which I attempt to actually solve the puzzle, because that feels like that feels worthy. I feel like I might not be able to solve the puzzle from here, and all of that logic we've just done will just be lost forever, and I will feel sad about that. Okay, I don't know what to do. I sort of do want to stop the video, make this a two-parter, but let's try and carry on. So now we know that one of the rings of this puzzle, let's get rid of the corner greens, one of the rings is 9-less. And we know it's not the outer ring, because the outer ring contains 4 Sudoku units, so it's definitely got at least 2 9s in it. So one of these rings, well, it must surely be the Phistomefel ring that's got no 9s on it. That must be true. I'm just alleging that because it just feels harder to miss a 9 out of this ring. But how do we prove that? If one of them has no 9s on it, so if there were 4 9s on this ring, then you get 4 9s in the corners by Phistomefel. So we'd have 9s in those cells. We'd have no 9s in the middle ring, because that's what we're alleging. You'd have 4... Oh, yes, of course. Hang on. The corollary... Yeah. This is... My brain is catching up with me now. Right. So the corollary of there being a ring in the puzzle with no 9s is that 2 of the rings must have 4 9s, because we can't put more than 4 9s in a ring. So the 8 9s in the outer rings are entirely within 2 different rings, obviously, but also there are exactly 4 in those rings. So this is important for this outer ring. So in the paradigm, or in the hypothesis that there are 4 9s on the Phistomefel ring, let's just put those in. Let's put them there. I think that's fair. Oh no, that's total nonsense. What on earth are you doing? Shows how much I think about Sudoku. I don't even like. No, I don't like putting them in the middle. I think it just feels wrong, doesn't it? Let's put them sort of offset like this. This gap is going to be very problematic if it was anything like this. But if we put 4 9s in the Phistomefel ring, we now have to put 4 9s in the 2x2s in the corner by the Phistomefel theorem. And because you've got to put 4 9s in the perimeter, you can never use a corner cell. So actually, this is very interesting, because I think you'd actually force the position of all the 9s. Which actually might mean this is correct, because it's a way of actually forcing the positions of digits. But what's wrong with this? Or what's right with it? What's right with it is that it looks at first blush like it works. What's wrong with it? We would know that I think the only tension I'm seeing here is that the gaps between the 9s in the Phistomefel ring can't be that big. So if this was true, we'd be saying that that string, for example, added up to the same number as that string. And that looks tricky. It's obviously impossible here, I think, because 1, 2, 3, that's a 7-cell string, isn't it? So the triangular number for 7 is 28. So what we'd be saying is that the gaps between right. I can disprove this. I can disprove this quite elegantly, I think. Okay, this doesn't work. So let's go through the logic here. If we put 4 9s on the Phistomefel ring, then because I think it might be because of this given 3, but because they're in this hypothesis, we know there are no 9s in blue, and there are 4 9s therefore in the outer ring. The positions of those 9s are absolutely forced by Sudoku and the theorem. Now, why does this matter? Well, it's because these 9s are at least, well, they're exactly 7 cells apart. And the triangular number for 7 is 28. Now that means that in terms of the middle ring, these little strings of digits are each adding up to 28. And the ring overall is adding up to 4 times 28 plus 36. Why do I think this is impossible? Well, because the implication of that is that this sum, the sum of these digits that we're stacking along the lines and in these 9s here, is the same number as we can put into these 2x2s in the corners. Well, these 2x2s in the corners are, well, in fact, in this puzzle, they're not this, but the maximum they could ever be would be 6, 7, 8, and 9, which is 120. So if I maxed out every 2x2, I would get 120 in these outside bits. But here, we know we're multiplying, what would it be? At least 28 plus 9 by 4. So we're multiplying 37 by 4, which is way more than 30 times 4. So it's absolutely impossible, but I am appreciating that this relies on everyone believing that the Phistomefel ring is a legitimate technique. And it is a legitimate technique, and I am now convinced. Well, I think that proof is interesting enough that it's worth me actually just proving it for anybody who's watching this video and who isn't aware of Phistomefel. I can do it in a couple of minutes. If you've seen it before, I apologise, but on Cracking the Cryptic, we always try and be new viewer friendly. So the way to prove Phistomefel is like this. Let's describe those purple cells. When I say describe, I mean I can state now absolutely precisely what the content in general of those purple cells is, because that's a complete row of the Sudoku, that's a complete row of the Sudoku, that's a complete box of the Sudoku, and that's a complete box of the Sudoku. So the purple cells in any Sudoku contain 4 sets of the digits 1 to 9. Now imagine you wrote those four sets of the digits 1 to 9 onto individual Scrabble tiles and put them in a purple bag. Our purple bag would have 36 tiles in it, and if we examine the tiles, we would find 4 tiles that had the digit 1, 4 tiles that had the digit 2, etc., all the way through to 4 tiles with the digit 9. Now, how would we describe a different bag that we're going to create now with a different set of tiles in it? Those green tiles, well, that's a complete set of the digits 1 to 9, that's a complete set, that's a complete set, and that's a complete set. So if I was to go and create a bag of green tiles with these green digits on them, they would have identical composition to the purple bag of tiles, because there would be 36 tiles in my green bag, and there would be 4 1 tiles because there's a 1 in each of these columns. There would be 4 2 tiles, etc. So the bags contain the same thing. Now, let's say I rummaged around in my purple bag and I found whatever this digit happens to be. Well, and let's say I rummaged around in my green bag and I found that digit in there as well. And I took those tiles out of each bag and I threw them away. What could we say about the 2 bags then? Well, each bag would then have 35 tiles in it, but they would still have the same makeup, because they had the same makeup before I did anything to the bags, and I've just thrown the same digit out of both bags. So as I can do that, obviously, for any tile that appears in both bags. So these can be removed from both bags of tiles, and there you go. you get left with a purple bag with 16 tiles in it, a green bag with 16 tiles in it, and the composition of those tiles will be exactly the same. So that is the proof of Phistomefel, which I've just needed to... I've got nothing in the grid, good grief. I've just needed to prove that there are not 4 9s on the orange ring. Now, I know that there's at least... Well, because I know that there are 4 9s on 2 of these 3 rings, and I know it's not this one, I now know that this puzzle has 4 9s in the blue ring and 4 9s in the grey ring. That is what I know. I wish I knew what that meant. What does that mean? I know there are no 9s in the Phistomefel ring, so I know there are no 9s in any of these positions in the grid. So I know the 9s in the corner boxes, therefore, because there's no 9 in the Phistomefel ring, and that means there's no 9 in the 2x2s in the corner, that each box has a 9 in it. So there's a 9 in one of those cells in box 1, and there must be the mirror positions in each of these boxes. So there are 9s in those positions. Right. I've got a clue what that means. So, and then in these boxes, in the even numbered boxes, I just can't put a 9 in the orange squares. So these are going to have 9s in these positions. So these are all, every cell that has a 9 in its corner is a possible position of 9 in this puzzle. But am I actually any closer to knowing what the value is of the sum between the 9s? And I fear the answer to that. How do I ever know this number if I don't know what the total of this is? Because I need to deduct something from 288. Basically, I need to deduct from 288 whatever goes in that ring. And then I need to divide that by 8. And then we're in clover. Then we know what's going on. But that implies there's some way I can know what's in that ring. How can I know that? I wonder if it's something to do with making assumptions about what we put in the corners here. Okay, yeah, let's do that actually, because I'm just realizing now that the fact that there's no 9s in the corners does mean that I know for a fact that if I was to max out the value of the corners, I'd have to put 8s and 7s in, wouldn't I? Because I can't use 9. Yeah, okay. So let's work out what the maximum and minimum is that can be between the 9s in the perimeter of this puzzle. Because we can do that. Because what we can do, 7 and 8 is going to give the... that's going to give the smallest number, I think, of the value between the 9s. But if I was to put, instead of 7 and 8 in the corners, if I put 1s and 2s in the corners, then we can say that the perimeter of a Sudoku with 1s and 2s in the corners would sum to 174, because it must be 180, which is 4 rows and columns, minus the overlapping digits, which would add up to 3 on each side. So we'd have 174 between 4 nines, wouldn't we? Is that right? Yeah, so I'd then have to deduct from 174 those 4 nines. This is getting really complicated. I'd have to deduct from 174 those 4 nines. So that's 138, isn't it? And then 138 divided by 4 would give me the number, which is what, 30, it's not even it's like 33 or something. That can't be right. That seems far too big. I normally resist at all costs using notepads in these puzzles, but I think this one I might actually have to. 174, 144, 138. 138 is, we are dividing by 4 there, aren't we? I think we are. 138 divided by 4 is 3, 4, so 34. It's 34 and a bit. Okay, well, that's, so 34 and a bit is what is at one boundary. What's the other boundary then? So if we instead put not 8s and 9s, we can put 7s and 8s as maximum into the corners. Then we've got 30 in the corners. So we've got 180 minus 30 is 150. But then we have to deduct the 4 9s from that. So we've got 114. And then we've got 114 divided by 4, which is 20. What is it? Oh gosh, why can't I do that quickly? 34, 28, is it? 28 and a bit. So it's 28 and a bit. So we've got to do more than 28. So we've got to go 29 on one side as the boundary. So the minimum value of the difference between the 9s is now 29. And the maximum value, I've now forgotten. It was 30 something. What number was it? Was it 138 divided by 4 or something like that? It was something like that. I think it was 34 or 30. Maybe it was 34 or 35. So we have narrowed it down. We have narrowed it down. And we know it's quite a chunky number, because it's at least 29. 29 is quite a chunky number. So that means it's at least, yeah, let's just think about that. So if this was 9 and this was 9, then we would be saying those 4 cells have to add up to 29 without using 9. That's not going to work, is it? Oh, no, actually, what about if you did double 8? 16. Oh, you rotten thing. Even that's complicated. Look, that can work. So you can do it in 4 cells. So actually that's not as big a restriction. I was thinking, because 29, I normally think about it as 5 plus 7 plus 8 plus 9, because in the same row of a Sudoku, or the same, if you can't repeat a digit, that's the only way of doing it. But here, because we can go round corners, we can repeat digits, so you can get to 29 quite easily. So, okay, that's not a massive restriction. Right, so what do we have to do then? Do we have to try and do that same thing on the middle ring? I am not looking forward to that. So, how do we do that then? So what we're trying to do is work out trying to work out what is... Do I want the minimum value or the maximum value of this ring? I feel like I must need the maximum value of this ring, because inevitably this ring has got less digits in it than this ring does. So what I need to know is what's the maximum difference between nines that is possible on a middle ring of a Sudoku. Now, if I'm going to maximize that, I need to have high digits in the ring, which means I need to have low digits outside the ring. So I need to do something like this, don't I? Let's actually use a big digit. So let's say I miss out the lowest digits I can from this ring. And then if I'm going to maximize the total for the sum of these digits, I need to have as many high digits in it as I can, which means I must have low digits in the corners. So each row and column I'm going to say contains the digits that are not 1 and 2. So it's going to have 7 digits, which are 9, 8, 7, 6, 5, 4 and 3, which add up to 42. And I'm going to put piddly little digits in the corners in order to keep those corners down. And I've got a 5 in one of the corners. So I can have 2 3s, a 4 and a 5 in the corners. Right, so what's the maths of that then? What's the maths of that? So we've got 42 times 4, which is 168. But I've got to deduct from that the corner cells, which are adding up to 3, 3, 4 and 5, which is 15. So I'm at 153. But I now know that there are 4 9s in there, which add up to 36. So that's 1, 2, 3, 117. So 117 divided by 4 is the absolute maximum value that I can put between 9s on the middle ring. So 117 divided by 4 is what? Is 20. Oh yeah, come on, that's good, because 29 was the minimum on the outside. Hang on. 117 divided by 4 is 29. It's 29, isn't it? It's a smidge over 29, but you can't get to 30. This is it. We've done it. We've done it. Holy moly, moly, moly. Right. This is unbelievable. Right. Right. So let's check the logic. What we have worked out is that we've worked out the minimum value between 9s that we can possibly put on between 4 9s in the outer rim of a Sudoku is 29. That's the absolute minimum. But we've worked out that the absolute maximum that we can have between 9s on the middle ring is 29 as well. So we have reached equilibrium. So the number is 29. Now, so the number is 29, but the number is 29. Sorry, I know I'm repeating myself. I'm trying to think clearly about what this means. So that I think means, but I never got exactly, because exactly 29 is 116, isn't it? Is the digits that are in this ring that are not 9 and this ring that are not 9 are in each instance 116. And I think the absolute maximum I was able to get here was 117. So there is a tiny degree of freedom. Oh, no, there isn't. There isn't. Oh, this is so beautiful. Right. So there is not a degree of freedom because of the given 3. I said, because I wasn't looking at the grid when I said it, I said that in the corners of this middle ring, I could put the digits I put 2 3s in. I put 2 3s in the corners in my maths. I did. I was thinking this was possible. It's not possible. There's a 3 here. So you can't do that. So the maximum digits you can actually put in the corners are well, I could put 1 3 in up here. That's the best I can do. Sorry, not the maximum, the minimum. I think I said maximum, I mean minimum. The minimum digits I can put in the corners. I can put a 3 here and a 2 4 pair in this row, I think. Although that wouldn't work with obviously a 1 2 pair there and there. That's not going to work. So I'm going to have to jiggle around with this a bit. Hang on. Let me think about this. I think we're onto something here. I think this middle ring, I think, is completely fixed if I can figure out how to do it. So how do we do this? We've got to maximize. Definitely got to maximize everything I can that is not in a corner. So let's get rid of these 9s and try and max. So these digits maximized would be 4, 6, 7, 8, and 9. These digits, and that would be the same there, 4, 6, 7, 8, and 9. Now, these digits maximized could be 5, 6, 7, 8, 9. And these digits maximized could be 5, 6, 7, 8, 9. And now, the corners. I need to minimize the corners, having made sure that, yeah, because I never want to introduce sort of a 1 in here, for example. Because I need the most I can in this ring. So I need the most I can in this ring, subject to the fact that once I've stocked this full of the maximum digits I can put in order to make sure that I'm not, say, because the moment I put an 8 in a corner, I'm removing my ability to have an 8 on this string and an 8 on this string, and it's a disaster. So I need to put the least offensive digits in the corners. So this corner could be the least offensive digit. That would be a 3. And then I could put a 1 here, and I could put 2s and 4s into those squares, and that would have to be a 2 because I want to put a 4 in this string of digits, and that would be a 4. And that, I think, is optimized. So what is the sum of all of this nonsense? We've got 35 there, 35 there, that's 70. Plus 34 plus 34, so that's another 68. So that's 138. 138, 140. 152 is where we're up to. So I can make the perimeter 152 at an absolute maximum. And 152 minus the 4 9s of 36 is 116. And 116 divided by 4 is 29, and that is how to do it. That is the answer. This is the answer. Well, this is not only is this the answer, this is giving me digits because these digits must be correct. Let's just double check that. Let me just double check that. I think this is forced, absolutely forced. I mean, if for example, I said, okay, I've got some degree of freedom here, which I don't think I do, and I was to change the 4 in there to a 3, say, in order potentially to allow me to put a 4 here in a corner. But now by reducing this, that's not a good thing. I've got to be now, yeah, so now this would come down to 2 because it couldn't be 3. And I think I've lost too much here now. Yeah, I've lost too much because effectively what I've done there is I reduced this by 1. And I've got the same numbers in those 2 cells that I had before. So all I've done is managed to get to 115 now, which is not enough. I need to get to 116 because I need to get to 29 as the gap in order to fulfill the requirement that the outside is even possible. So this doesn't work. This doesn't work. This 3 that does it. It's absolutely magical. It's absolutely magical. It prevents us from using double 3 in the corners here. So this is totally forced, and I've got to have a 1-2 pair here. I've got to have a 1. I've got to have 3 here by Sudoku. It can't be a 1, and that means this is a 1. This is a 2. This is a 1. This is a 1. This is a 2 by Sudoku. I've now got digits in the grid. Now I've got digits in the grid. We know the number is 29. And all we've got to do now is figure out how to do the rest of the puzzle. Still not knowing where any 9s go. But now at least I know that I'm heading up towards 29, so it's presumably 876. Yeah, so like that cell, for example, that cannot be a 9. Because if that was a 9, there's no way to make this string of digits add up to the right number, because these digits are now 8764, which is 25, and if I add 5 to that I get 30, not 29. So I don't think that can be a 9. Yeah, we might be able to do that by looking at these digits. It's going to be much harder when we look at this digit, for example, because we can't see what that digit's restriction is. It doesn't see this 9. So maybe that's the way we do it. Maybe we eliminate... Yeah, this could be interesting, actually. Yeah, okay, let's see. So if that was a 9... Now I want to look along here because I know that these would then be 8765, which is 26, I want to say. 26 and 4 is 30 again. That doesn't work. So that's not 9. This one, that would give us 26 and 2, which is 28, and I can't put a 1 there. That doesn't work. So this looks profitable, actually. This one, if that's a 9, I've got to put 20. Oh, that works. Okay, that's annoying. If that's a 9, these, and we took exactly that string of digits, we would get to 29, I think. I'm just going to double check that. 8765 is 26 and 3 is 29. This would be a 9. Oh, bother. Although maybe, is it hard to go the other way? Yeah, actually this is okay, I think. I don't think this can be a 9, not because of what happens vertically, but maybe what happens horizontally. I need to get a string of digits here that add up to 25, and that doesn't seem possible. 8, 7 and 6 is obviously already 21. I need another 4. There's no combination that gets me to the right number. So actually, if I look down, I have the same problem with that. It's just more complicated. So this one, I think this one's going to have the same problem with the 4 here. I think the 3 is the interesting number. If this is 9, this is 8, 7, 6, 5, which is 26, and 4 is 30, so that is not 9. If this is 9, this 3 isn't involved. It's going to have to have a 5 with, oh, but hang on. If this is 9, we've got 8, 7, we've got 25 here. Yeah, and 5 is 30. It still doesn't work. So now, this might be interesting, because what I could see this is going to do is, if you look at boxes 2, 4, 6 and 8, the 9 is locked into these little strings here, which means that in the perimeter, the 9 is being knocked out of the edge. And that is getting us to a position where these 9s look very interesting, because there can't be that many ways of arranging these. They've got, yeah, there's only 2, isn't there? What if this is 9? Where is the next 9 in the grey? Well, it's not there, because those 3 digits would have to add to 29, and that's impossible. So it would have to be here. So that is one arrangement of 9s. And the other arrangement is going to be those. So those would be 9s with... So one, either red or green is correct. And that means what? Can we do something with that? So if these 2 were 9s, this string of digits here would add up to 29, which means that that cell would be a 7, I want to say. Let me just check that. So what I'm doing there is I'm saying, if we know, if greens were 9s, these would add up to 29. 29 minus 1 is 28. This row overall adds to 45, and I've got 28 here, plus 10 is 38, so that has to be a 7. So one possibility is that this is a 7, and then oh, come on, you're kidding me. That is so lovely. This doesn't work. I hope reds work. Let me just think about reds for a moment, or I've made a mistake in the puzzle. That would be 20. Oh no, I think I've made a mistake. I definitely see with greens, I think I'm going to get 1s in all the corners, but I think with reds I might be getting, not 1s in all the corners, I get 7s in all the corners. And I think I might be getting the same with reds as well. Because even though I knock 2 out here, I replace it here. And I think that's a 7. Oh, that's so annoying. I thought that was so beautiful. Look, because the 9s are always in identical positions relative to the 1s going around the grid, the green 9s, the logic that gave us this as a 7 just propagates, and you always get a 7 in the corners. Now, that is a problem, because so if you have green 9s, you have 4 7s in the corners. But I think the problem, and that's obviously impossible from a Sudoku perspective, but I think the problem is that with the red 9s, I'm getting the same thing. That's certainly a 7. This one isn't a 7 actually, so maybe that's okay. If this is a 9, well, I know that green 9s are impossible. I'm going to get rid of those. I need red 9s to somehow work. Now, if this string of digits adds up to 29, 29 minus 2 is 27. 27 and 12 is 39. That would be a 6. Now, this is a 3, so that means this string of digits is going to add up to 26. 26 and 12, that's 7s again, isn't it? 26 and 12 is 38, that's 7. I need this not to be a 7. This string of digits is 29, so that string of digits is 26. 26 and 11 is 37, and that's an 8. Oh, come on. Oh, good grief, it works this way round. Oh my goodness me, that is so pleasing. So it breaks with the green 9s because of the 1's position, but somehow the logic, somehow when you do it the other way, because there's some different digits in these positions, the ones that aren't 1s, the symmetry gets broken, and you end up with the same total, which shouldn't probably be surprising. No, it's not surprising, is it? Because we know that, yeah, it's not surprising at all. So we're always looking for 28 in the corners, but the 28 is not made up of 4 7s this way. It has 6s and 8s in it to break and allow us to complete the rules of Sudoku, or not break the rules of Sudoku. So, see, this is quite a long video. I am not even remotely surprised. This is one of the most brilliant puzzles that you will ever see in your life. This is sort of, it's ridiculous. It's absolutely ridiculous. I have actually got a small slither of hope now that I might be able to solve it. Well, we have got digits at least, and we've got quite an understanding of how this works. But is that enough? I can put 7 into that row. Just notice using the given 7. That's got to be a 7, which means these are not 7. That's not a 7. Okay. That means what exactly? So I've positioned 4 of the 9s in the grid. I don't yet know about the 9s in this ring, unless I'm missing something. There's got to be a 1 in one of those. There's got to be a 3 in one of those as well, actually. That's a 1-3 pair. Oh no. It could well be a bit of Sudoku now. I mean, 1s have got to be in those 3. 1s have got to be in these 3. So the Phistomefel ring, I suppose, is being populated. In essence, we do know the composition of the Phistomefel ring now, because we know the 2x2s in the corners. I don't think that's enough, is it? So 2 I can place in, well, 2's in one of those cells, so it's got to go there. So maybe it is Sudoku. 2's over here. This square's a 5 or an 8. This box is really it's really interesting. Quite difficult for that square to be an 8, actually. If that's an 8, those 3 digits add up to 19, And we know that we're looking for 29, don't we? Now that means that whatever I add on, this way or that way or that way, has to add up to 10. And the only way that will work is if we use double 5. But unfortunately, that might be possible. Although that would put double 9 in those cells. And that feels like I'm going to run into that problem I ran into in the example where I put 9s in and they all looked at each other. Is that possible? Can you have 2 9s here? Because now I mustn't have a 9 here and I mustn't have a 9 here. Which means that I cannot have regular gaps of 5 digits between 9s in this situation. And that means one of the gaps has to be a 4-cell gap, and that's very difficult, or well, it can't be less than that. A 4-cell gap without using a 9 to add up to 29 has to be 8876, which means I have to go round a corner to do it, and I can't do that. It doesn't work. There you go, proved it. So this is not 99. I think that logic was sound. I'm just going to double check it. So if you try and put 99 in the middle of these, obviously we can't put 9s in these positions now. And that means that either this is going to have to be a 4-cell sequence, for example, or it's going to be a 6-cell sequence. But if this is a 6-cell sequence and we put the 9 here, the corollary of that is that we're going to have a 4-cell sequence in one of along this string somewhere. Now, the problem with a 4-cell sequence that must sum to 29 without using 9 is it has to be 8876. The 88 means you can't just do it with 4 cells like that. We have to bend round a corner. But none of these corners has a 7, 6 or 8 in it, so you can't do that. Therefore, I think it is safe to say this is not an 8, this is a 5, these are not 9s. In fact, does that logic is actually quite good. Let's forget about this being a 5, which it is. These cells are simply not. They're simply not able to be 9s, because the moment I make one of these a 9, I get the problem that because I can't have regular 5-cell gaps, I have to have a 4-cell gap. A 4-cell gap requires a corner that has a 6, 7, 8 or 6, 7 or 8 in it, which is possible in this particular puzzle. So these cells are not 9s. These digits are not 9s. This is a 5, so this is an 8. Now I know what these digits are. These digits are 2, 4 and 5. So these digits are not 5. So this digit I now know, apparently. This is a 5. This is getting quite exciting. There's a 5 over here. These digits are 4, 6s and 8s. This digit is not an 8. Now, all of these digits are not 5s. So now I've got 16. I need 13 more. Ah, this is it. I'm going to get all the 9s, I think. How do I add on 13 to this? Well, I can't take one from each of these, because if I take one from each side, I've got to put double 9 in here again. We've just proved that doesn't work. So I have to get my 13 either from those two cells. Well, they don't add. There's no option there that adds to 13, or those two cells, Well, that does work with 6, 7. So I think that's forced, and this is the 9. And once this is the 9, we're away. This is not 9 anymore. 6, 7 means this is 8. This is not 8 anymore. But now we want to maintain a regular gap, don't we? So this must be a 9. 3, 4, 5. This must be a 9. And this must be a 9. And let me just have a look at this in a second or two. So now what? So now I need to make these add up to 29. These add up to 29. And I can get that digit, can't I? Because these digits add up to 14 and 7, which is 21, and that's an 8. That is an 8. There we go. Now these are not 8, which means I know these are 4, 6, 7, which is 17, and 5 is 22. That's a 7. That's not a 7 anymore. These don't have 7 in them anymore. Oh, so this is okay. So we just have to check the maths on this. We've got 11, so I need those to add up to 18, and they do. This is so clever. How do you set this though? How? It's completely ridiculous. Those are 4s, 5s, and 6s. 4, 5, 6 triple in this row. So these 4 cells now are other digits, 1s, 2s, 3s, and 7s. So this is that right? Is this a naked single? I think this row needs 1s, 2s, 3s, and 7s. 1, 2, 7 there. That's a naked single. 3. These digits are now 1, 2, and 7. 3 has a home in one of these cells. This digit is 4 or 6. Doesn't seem to be resolved. Oh, yeah, look, I've got a 4, 6 pair in column 7. So those digits are known now. These are 1, 2, and something. No, not 1, 2, and 4. 1, 2, and 8, maybe? So I'm beginning to think we're going to have to use this in a minute, which is a bit terrifying. Oh, look. I've got 8 9s in the grid now, of course. And if I've got 8 9s in the grid, I really ought to be able to place the 9th 9. There is a 9 in the middle of the puzzle. So this ring is 1, 2, 3, 4, 5, 6, 7, 8. That is what we now know for sure. And there's probably, there's going to be stuff like this. You can't put 6 and 7 in this string. So I think there are going to be restrictions on this. Let's just check whether we can do more with Sudoku before we embark on the madness of the yellow ring. That's not a 7. These digits are 3, 4, 5, and 6. These did, yeah, okay, maybe we have to get full Goodliff on this. 3, 4, 5, and 6 here. 5 and 3. I can't quite see. 4, 6, oh no, there's a 5 in one of these two. It doesn't seem to get resolved. That's not 6 by Sudoku. So these digits are 2, 4, 5. Oh, 2, 4, 5, and 8 again. Oh no. I'm going to do it. I'm going to pencil mark these as well. I'm sorry. This one's going to be horrific as well because there's actually 5 options down here. 1, 3, 4. Sorry, 1, 3, 4, 5, 6. I think is what we're looking at. That's really horrible. That doesn't seem to see anything good, does it? So, how do we use this ring? We know this ring is a sequence of 1 to 8. But we don't know where it starts or finishes. We know that We know that this side of it has no 7 on it because of this 7. And we know this digit here is not a 1 or a 2, because if it was a 1 or a 2, it would have a 1 or a 2 on the other side of it and break that cell. So that digit is restricted. This digit cannot be 1 or 2. I think it might be able to be 3. I'm not certain about that. If it was 3, this would be forced to be a 1, because there would be a 2 on one side of it. I'm not sure I can rule out 3. 4 is not going to be under pressure. 5 is not going to be under pressure. 6 is impossible, because if it was 6, it would have a 7 on one side of it. So this is 3, 4, 5, or... No, and it can't be 8, of course, because if it's 8, it would need to have a 7 and a 9, and that would most certainly break it. So that digit is restricted. Now, if this is 3, 4, or 5, whatever digit you put in here, there is definitely a 4 in that sequence, and that means I can get rid of a 4 from here and a 4 from here. And that is very annoying. Just seeing how long this video is. It's nearly 1 hour 30. Good grief. This is definitely one of the hardest puzzles that, well, I think I've ever solved, frankly. I haven't solved it yet. But I am hopeful I'll be able to. If I sit here long enough from here, even if I have to bifurcate, which I would never do, but I do think it must be solvable from here. If there's a 4 on this side, doesn't that mean there's an 8 on that side? Is that nonsense? I don't think it is. 5, 6, 7, 8, 4, 5, 6, 7, 8. Yeah, there's always an 8. There's always an 8 on the opposite side, so that means I can do more pencil mark removal. I think that follows. Well, I mean, it does follow. If there's a 4 in one of these on a thermometer that's sequential, the 8 can never be that near the 4, obviously. So I think the 8 gets shunted over into these cells, sort of by symmetry almost. There's a 4, 6 pair here. This becomes an 8. That's beautiful. That gets me an 8 and a 6. That 6 is going to be interesting, actually. Well, for no other reason that this can't be a 4 anymore. Because if that's a 4, whichever way round the thermo goes, it's either going to go 4, 5, 6 or 4, 4, 5, 6. And you're going to end up with a 6 in this column. So this square here is not the 4, which means this square here is not the 8. And parity is now important, presumably, because now we're getting there. Now this cell is odd, and that means that cell must be odd, and that cell must be odd around a thermometer that's changing parity every cell it moves. So now these cells, these 4 cells in the corners, are 2, 4, 6, and 8, and we know that these are not 8. We know these are not 4. And these cells have therefore got to be 1s, 3s, 5s, and 7s. And presumably this one can't be 3 or 5, can it? Because it would be 2. Yeah, if this is 3 or 5, it's too far away in terms of sequencing. If that's a 3, that implies that's a 5, and I need to put 4, 4, 4 along there, and that's not going to work, is it? So this digit here is 1 or 7. But I don't think that's going to be enough unless we can... Right, let's see if we can use this 5. We can get rid of a 5 here. We can get rid of a... Oh, this isn't a 5. Sorry. That was me doing my example. This isn't a 5. This is a 3 or a 5, so I can't do anything with... No, I can't. 1. Where does 1 go in that column? There. We can... Does that matter for that digit? there must be something here now, I think. If that's 3, this is 5. That's 6. This would be 2, 4. Hang on, I've now lost track of where I started with that. I think I said if that's 5. No, I didn't say that. I started off with that being 3, didn't I? If that's 3, 2, 4, that's 5, that becomes 6. That all seems to work. I think it works either way round. If that's 5, that's 4, 6. That's 3. And that's 2. Yeah, it does. Okay, sorry. I want to say this can't be a 6 now. Is that true? If that's a 6, this has to be 7. And that's going to break that cell. So that's not right. This isn't 6. The same must be true. No, the same isn't true there. That's so annoying. Because the 6 could go to a 7 here. So this is 2 or 4. 6 has still got 2 places in the column. How do you do this? I think it's either this digit or this digit that's the key. I'm going to check this one. I checked that one already and that couldn't do anything with that one. Right, if this one is, which way round is going to be more difficult for it? Right, okay, I can disprove this from being a 7, I think. It's not easy to see this, but I can disprove this. I think it ends up with a 5 here and a 5 here. Let me show you. If that's a 7, the point is that this becomes a 6-8 pair. Now that means 2 things. It means firstly, this is a 7, so this is a 2, but also this is a 4, and that's making this a 5. But also we have to think about what's the effect of this being a 7 on this digit. Well, that's going to be a 3, can't be a 5. So if this is a 3, we must have 2 4 flanking the 3, and that is also a 5, and that doesn't work. I am fairly confident that that is not what Nihilian had in mind. But at 93 minutes into the video, I think you have to forgive me, though it's certainly logical. It's not bifurcation because I could see it without doing it. So I'm going to do it. That is a 1, which is lovely because that means that's a 1 and that's a 3. And it means that must be a 5 now to be far enough away from my 1. That means this is a 2. This now must be a 4, which means this is a 6, which tells me the order of the thermo. 2, 6, 7, 8. I've done the middle box. I've done a 3 here by the power of magic. I've done a 2 here by the power of Sudoku. How do we do? I want to do this column, please. Please don't be any more hard steps. That's a 4 by Sudoku, so that's a 6, that's a 4, that's a 5, that's a 6, that's a 4, that's a 6. Oh, please keep going. 6 comes out of all of those. 1 comes out of here. 3 and 4 come out of here. 5 comes out of here. 2, 1, 8. 2 and 4 come out of there. There is a triple in that row, I've just noticed. I'll come back to that if we need to. That's not a 4. This is not a 4. This is not a that's a 7. There we go. 7, 7, 6. So this is not a 6. Something must be going on in this row, surely. That's not a 5. That's not a 4. Still, I've got a 2-8 pair and a 3-4 pair. Don't believe it. Ah, right, this row. Look, I've got 1, 5, 8 triple, which must affect this. So this is a 6. Okay, so that's a 4. That's a 6. That's a 3. That's a 4. That's a 5. That's a 4. That's a 1. That's a 3. Oh, please. 8, 2, 1. 8, 5, 2. 3. That's a 5 by Sudoku. I've done it. Have I done it? Please let this be right. I did it. I did it. It took me ages. I'm so sorry to waste your times like this. Oh my goodness. 96 minutes. 96 minutes of madness. That is amazing. What an amazing puzzle. That... I can't believe I solved it. I can't believe it exists. It's ridiculous. It's ridiculous. It's the most amazing sequence of sort of logical steps you can go through to actually discover that this pattern exists of 9s and that it can force a solution. How did you even think that you could do it with 3 givens? This is one of the greatest things you'll ever see. I was going to say on the channel, but that's not true. This puzzle is one of the greatest things you will just ever see in your lives. It's mind-blowing. Mind officially blown. Nihilian, take a bow. I'm going to go and have a quiet cry. And thank you very much for watching. I look forward to the comments. I hope that they're kind. See you later. I'm cracking the cryptic.